So let us resume. There is one small mini chapter we will finish now before we move on to an exciting topic next week about dynamical systems and computation. We will finally connect everything together, dynamic self-replication, and we will study what does it mean for a dynamical system to compute or to simulate other systems. So this mini chapter will be extremely relevant for that. It's not just that I want... It's like a pretty standard notions from, algebra or dynamical system theory, but we will actually really need it next week. So this mini chapter can be called Subsystems, Embeddings, and Factors. So I could just formulate all of this just in the language of cellular automata, but it will actually be nice if we have this more generally. So in this section, I will talk about XF being a topological dynamical system. And what does it mean? It literally just means that X is endowed with some topology and F is a self-map that is continuous. So for instance, every cellular automaton is a topological dynamical system, but you can have continuous and smooth topological dynamical systems, and it will work just the same. So that is X is endowed with a topology and F is continuous. So fix two of these. Two topological dynamical systems. So what does it mean for X? Or maybe we can also call them A and B. They deserve a name. What does it mean for A to be a subsystem of B? It's very natural. So A is a subsystem of B if X is a subset of Y is closed and is closed. And if F is just a restriction of G to this subspace X. Which
of X and Y is closed?
Well, X is closed in the topology of Y because it's a subset. Y is closed because it's the whole space of Y. So the only interesting one is if X is closed. So we can already start with an example through another definition. This will be a cellular example. So let S be a finite set and F a finite set of patterns in S to the Z to the D. Then F defines a subshift of finite type sigma F to be exactly those configurations that avoid each of the patterns in F. So C does not contain any pattern in F. So an observation that will be your exercise, or it is already, it's been instantiated in the exercise sheet. Essentially, sigma F as a subset of S to the Z to the D is closed and invariant under all shifts. This is almost embarrassingly easy. Essentially, if a configuration does not contain some pattern and you shift it, then it's still going to not contain the pattern. So in some sense, this is a first natural example of a subsystem. So let S to the Z to the D and sigma V be a shift CA for some vector from Z to the D, and let sigma F be some subshift of finite type. So we'll abbreviate it by SFT. Then sigma F induces a subsystem of this CA. So it will often be useful to only study subsystems up to isomorphism. So we did define isomorphic dynamical systems, but now that we have a topology, let's strengthen the definition. And we will call it conjugacy instead. So A and B are conjugate. If there exists a homeomorphism H from X to Y such that we can first apply H and then G or the other way around. So if you like commuting diagrams, we can also draw it like this. This is Y. Here is G, and here is H. So you will also have a chance to understand what are some basic properties that are invariant under conjugacy, but it's pretty natural. So now we can talk about subsystems up to conjugacy. So we can say that A embeds into B if A is conjugate to some subsystem of B. So especially, this will be kind of important for us, is that let X and Y, so let's lose the generality for a second and let's assume that they are compact metric spaces, for instance. Then A embeds into B. If and only if there exists a continuous injection iota from X into Y, such that we also have a commuting diagram. So either we first apply F and then embed, or we first embed and then apply G. So similar diagram. Okay, I cannot draw these arrows rotated, it seems. G. And iota should not have the dot. So it's pretty natural. We have this system B, so there is Y, and inside of it there is some subsystem Y prime. And if this is conjugate to some X, so here we have G, here we have F. So if really A is conjugate to some subsystem of B, then there is this conjugacy from X to Y prime, so which is especially also a continuous injection, right? So that should be pretty straightforward. So maybe let's suppose the other way around. Or should I even write it down? So essentially, suppose we have this iota which embeds X into Y, is a continuous injection. So we have X, this is embedded, I just cannot do this, it seems, into Y. So we can define this subsystem to just be the image of X under iota, and it's very easy to check that this is really, okay, invariant under the map G. And then where you use compactness is to show that actually iota has a continuous inverse on this image, and that this already also implies that the image under iota of X is closed in Y, and that's it. And then the dual notion of an embedding is a factor. So we say that A is a factor of B if there exists a continuous surjection P from Y onto X, such that we also have a commuting diagram. So we can either apply G and then project, or we can first project and then apply F. So in the diagram sense, now we have Y onto X. So maybe an example, a rather trivial one. So let A be some d-dimensional CA. And let O be, not a set, but also a CA with a single state. So then it's very easy to show that O is, let's say, a trivial factor of A, where the P, which we call P the factor map. So the factor map just maps every possible configuration onto the one configuration here. So then O is a factor of A. Since P so for instance, 1 can be a set containing just 0, sends every possible configuration to this one configuration. And then it's pretty clear that the diagram really commutes, because no matter what A does, it gets projected to this one configuration where the O map acts as identity. So, in some sense, this allows us to compare dynamical systems. Essentially, if system B contains system A as a factor or as an embedding, it somehow means that B has a richer dynamics than A, because it can do everything that A can, modulo the factor map or the embedding map. But an example which is maybe important to mention is that if we only require from the conjugacy or from the factor map and the embedding to be somehow continuous and potentially have a continuous inverse, it does not guarantee us that a CA will only be conjugate to cellular automata. It can be conjugate to more general systems. So example, so let's say what this illustrates is that let A be a CA and let B be a general topological dynamical system. If A and B are conjugate, it does not necessarily imply that B is a cellular automaton. So it should be pretty intuitive why, if A and B are conjugate via some H, then we can express G to be H to the minus first F H. So it is pretty clear that G also has to be continuous. But what we don't have from the Curtis-Hedlund-Linden theorem is a guarantee that G also commutes with all shifts on its state space. So the example that shows this is, well, for instance, so let A be just the elementary CA corresponding to a left shift, be the and we now define some homeomorphism. So, and let H be a self-map such that H of C at position I is just Ci if I differs from 0 and 1. It is C0 if I equals 1, and it is C1 if I equals 0. So H simply just swaps the positions 0 and 1. It is easy to verify that it is a continuous bijection on a compact metric space and therefore a homeomorphism. So H is a homeomorphism. So let us define the map G. In the natural way, so we ensure the commuting diagram. Okay, so now our F is sigma. Then A is conjugate to this dynamical system we just defined via H. So we can call this system B. But B is not a CA. So all we have to show is that there is some shift with which G does not commute, and use the Curtis-Hedlund-Linden theorem. So maybe we can have a look at what G really does. So, what does G do? Suppose we start with some nice, well-ordered configuration. So first we apply H inverse. Since H is an involution flipping two positions, this is the same as H. So here we just get a configuration which is exactly the same everywhere except for at the origin where it flips the two positions. Then we apply the shift. So now everything gets shifted by one cell to the left. So we have C0. Maybe it's good to track where the origin is. So C1, C minus 1, C3, etc. And now again, the state at position 0 and state at position 1 get flipped by H. So we get C0. We get C2, which is at position 0, C0, C3, C1, C minus 1. So you can probably already intuitively see that G, there's no chance it can commute with an arbitrary shift. In particular, G composed with sigma is really not the same as sigma composed with G. So if we look at sigma composed with G for some configuration C at position 0, what do we get? So G itself would map the position C2 here, but now we shift this by one bit to the left. So this is actually C0. And if we look at it the other way around, then you can imagine first shifting this, so you can increase the indices of all of these. So then at the origin we will have C3. So for any configuration where these two states are different, we have that it is a witness of this non-commutativity. So indeed, G, okay, to the ZG is not a CA. So did we choose the wrong notion of conjugation factors and embeddings? Not necessarily. But there is a natural way we could have chosen a stronger variant. So we could have defined and sometimes in the literature it is required a strong conjugacy strong embedding and strong factor maps. Between dynamical systems which have some well-defined notion of shift maps on their space, but not necessarily need to be CAs. To additionally commute with all shifts. And then another exercise waiting for you is that this already implies that if A if A is strongly conjugate to a CAB, or is or strongly embeds into B, or is a strong factor of a CAB, then A is a CA. So maybe this seems more natural for cellular automata, but the following example shows that it is too restrictive. That we can have two cellular automata that are conjugate via a conjugacy that does not commute with all shifts. And such examples will be very important for us next week when we start talking about the computational capacity of dynamical systems. We will see there are different flavors to how to assess that. But one way is to see how many other cellular automata can a particular cellular automaton simulate. So we will again be somehow comparing the dynamics of two cellular automata. And this example I'm about to show you will be quite crucial. So this somehow shows that these strong notions would have been too restrictive for us. So this will be the last example of today. So our favorite CA that is easy to work with, let A. So now let's actually be adventurous. Let's do shift squared. B, the CA shifting every configuration by 2 bits to the left or by 2 cells. By 2 cells to the left. And let 2 to the power of 2 just be all sequences of length 2. So we define a map. We can call it O from 2 to the Z to 2 to the 2 to the Z, which O of C at some position n is simply C at position 2n and C at position 2n plus 1. So we can draw this because it is a very natural thing to do. So we have our configuration space of binary sequences. And what O does is it partitions this space using this tile being this rectangle of size 2 by 1, because we're in 1D, so it's not very interesting. And then mapping, essentially grouping each 2 consecutive states into one richer supercell, which is now living in this space 2 to the 2 to the z. So this is at position 0, this is at position 1, and so on. Is this clear? So what we can do now is let B just be a CA on this richer state space. So there will be now some abuse of notation. Now this shift is the shift on this richer state space, which shifts everything by 1 cell to the left. So sigma C at I is Ci plus 1 for C in this richer state space. And it is easy to check that A and B are conjugate. Indeed, if you start with any configuration C in 2 to the z, and you apply the sigma squared, which is the global map of our CAA. This is position 0. Then now we just have C2 here. If we pack this via O, we just get, this is at position 0. And now if we map this with the single shift on this packed space, now it views this as 1 cell, so it just shifts this whole cell, right, by 1 cell to the left. So now at position 0, there is exactly C2, C3, C4, C5, C0, C1. And that's exactly what happens when we pack the shifted space. It is also not difficult to check that O is really continuous bijection. So what happened here? We have literally just looked at A and rescaled the space by grouping together all cells into these supercells containing 2 original cells. And we have literally just constructed B to be the conjugation of A, which is just a CA acting on this richer state space. But you can easily check that O does not commute with all shifts. It only commutes with every second power of a shift, right? So essentially we have that. From this diagram, it is pretty clear that if we first do O and then we do shift on the packed space, it is the same as doing 2 shifts on the original space and doing O. So in particular, it will not work if we just shift by 1 cell here. It would not be aligned. So in particular, is different than O composed with sigma. So that's why for our purposes, it is maybe easier to not impose too much on the conjugations, vector maps, and embeddings, because we don't want to lose these examples where we can rescale the grid of a CA. and I will talk about this more next time, but I think we're good. I suppose you can start at 20.